Welcome to Review Lecture 1.8, Charges in Fields and Force on Charges. Upon completing this, you should be able to determine the force on a point charge from an electric field, determine the electric force on multiple point charges, determine the electric forces on a dipole. A force on a charged particle in an electric field. Consider a particle, charge Q and mass M, and a point inside an external electric field E, which has been produced by some other fixed charges or the source charges. This external electric field exerts a force F on Q equals QE. So if this is the only force acting on Q, it causes the charged particle to accelerate with A equals F on Q over M or Q over M times E. In a uniform field, the acceleration is constant. In a uniform field, of course, you can use the kinematics equations. In a non-uniform field, you would have to resort to calculus, which if you're not a Physics 222 student, that would be a problem, or energy. And just about anybody can use energy. And then we'll talk about energy later. Now, for a uniform acceleration, that is a uniform field, you can use the kinematics equations. And as a reminder, I've put them here, okay? And I'm not going to go over them, but you're welcome to look at these. It is important to get the feel of the equations. Other texts will use different symbols and often switch in the same text. Many will use S for distance and or displacement, a practice I dislike as S is used for the unit seconds. And these are good things to put on your cheat sheets for tests and homework. Get used to handling these and the units. I use these only for constant acceleration. For non-constant acceleration, you would need calculus or conservation of energy. Now, this is gel electrophoresis. DNA fingerprints are measured using the technique of gel electrophoresis. A solution of negatively charged DNA fragments migrate through the gel when placed in a uniform electric field. Because the gel exerts a drag force, the fragments move at a uniform speed inversely proportional to their size. This allows us to sort and identify them. A proton is moving to the right when it enters a vertical electric field. A very short time later, the proton's velocity is. Well, the proton is going to be deflected up. It's going to swim downstream in the electric field. So the correct answer to this is C. In a uniform electric field in empty space, a 4 Coulomb charge is placed and it feels an electrical force of 12 newtons. If this charge is removed and a 6 Coulomb charge is placed at that point instead, what force will it feel? Well, the force is going to be Q times E. So the E equals F over Q. So you take the 12 newtons divided by the 4 coulombs. That gives you the electric field of 3 newtons per coulomb. The force from that electric field then on the 6 Coulomb charge would be 6 times 3, and that would be 18 newtons. Okay, what is the magnitude and direction of the electric force on an electron in a uniform electric field of strength 3,500 newtons per coulomb pointing due east? The knowns for this and the unknowns are the electric field is 3,500 newtons per coulomb east. The charge is 1.602 times 10 to the minus 19 coulombs. What's the electric field? The physics of this is F equals QE, or E times E, 1.602 times 10 to the minus 19 coulombs, times the electric field strength of 3,500 newtons per coulomb, and that will be 5.6 times 10 to the minus 16th newtons west. The force on the negatively charged electron is, of course, opposite to the direction of the electric field. What is the acceleration on the electron? The knowns and unknowns are that mass is 9.11 times 10 to the minus 31 kilograms, and what's the acceleration? The physics of this is Newton's second law, and F equals ma. So A equals F over m, 5.61 times 10 to the minus 16 newtons times the units conversion divided by the mass of 9.11 times 10 to the minus 31 kilograms, or 6.15 times 10 to the 14th meters per second, and it's also west. An electron starts from rest near a negative plate and accelerates toward a positive plate. The positive plate is parallel with the negative one, and a uniform electric field of strength 1.85 times 10 to the 4th newtons per coulomb exists between the plates. If the plates are separated by a distance of 1.2 centimeters, an electron passes through a tiny hole in the positive plate. What is the electron's speed as it goes through the hole? Okay, the knowns on this of the electric field is 1.85 times 10 to the 4th newtons per coulomb. The initial position is 0 centimeters. Final position is 0.012 meters, and of course the initial velocity is 0 meters. The charge is 1.602 times 10 to the minus 19 coulombs. The mass is 9.11 times 10 to the minus 31 kilograms. It's a uniform electric field, so that means the acceleration will also be uniform. And we need to know the velocity. The physics of this is F equals QE, and that equals mass times acceleration. This uniform electric field, constant acceleration, kinematics, Newton's second law. And we can use B squared equals V naught squared plus 2A times X minus X naught. We solve this for A. A equals QE over M. And then we can say that V equals the square root of 2 times the electric field times the charge on the electron times the x divided by mass. So this becomes the square root of the quantity 2 times 1.85 times 10 to the 4th newtons per coulomb, that's the electric field, times the charge is 1.602 times 10 to the minus 19 coulombs, times the position, which is the final position, is 0.012 meters, and then divided by the mass is 9.11 times 10 to the minus 31 kilograms. The V is 8.84 times 10 to the 6 meters per second. This is about 3% of the speed of light, so we do not have to worry about relativity. If we did, we would have to use energy to calculate this. Okay, so what happens when you stick a dipole in an electric field? So shown as a dipole, electric dipole placed in a uniform electric field. The net force on the equal and opposite charges of the dipole, of course, will be zero because they'll cancel out. But the electric field can exert a torque on the dipole that will cause it to rotate until it's aligned with the electric field. Notice that the positive end of the dipole is in the direction in which the electric field points because positives like to swim downstream. The electrons love to swim upstream. So the negative charges are like fish returning to spawn. They swim upstream against the direction of the field. And the net effect of this is to cause this to align in this way, where the positive charge is in the direction of the electric field and the negative charges is pointing upstream. Okay, which dipole will experience no net force in the electric field? All three dipoles. The net force on any dipole in a uniform electric field is zero. It's a trick question. Which dipole experiences no net torque in the electric field? None of the above. Okay, the correct orientation would be if this one were flipped around. Because remember, this electron is going to want to swim downstream and this one wants to go that way. So there would be a choice D here where this was turned around. That would be the correct answer. But without that, it's none of the above. Okay, now dipoles in a uniform electric field. We place a sample of a polar substance, one with permanent dipoles like water molecules in an uniform external electric field. The field will exert a torque on the dipoles, which tends to align them with the field. All the dipoles rotate until they are aligned with the electric field. This is the mechanism by which a sample becomes polarized. If the field is made to switch polarity, the molecule will flip. Rapidly varying the electric field polarity will make the molecule flip rapidly and repeatedly. This generates heat, and this is how you cook your hot dogs in the microwave oven or warm up a cup of coffee. Torque on a dipole, Physics 222, calculus based only. The torque on a dipole placed in a uniform external electric field is tau equals 2 times the force on the positive charge times S, that equals Q2 times Q times E times 1/2 S sine theta. S is, of course, the distance between the charges. Tau equals QSE sine theta or PE sine theta, where P is defined as the dipole moment, which is Q times S. And we can rewrite that as tau equals P cross E. For the Physics 122 student, which is an algebra-based physics class, the torque on a dipole placed in uniform external electric field is tau equals 2 times the force on the positive charge times S, and that S is the distance between the charges, and that equals 2 times Q times E times 1/2 S sine theta. So tau equals QSE sine theta, and that equals PE sine theta. P, of course, is the dipole moment, which is Q times S. Example, two 1-gram balls are connected by an insulating rod of negligible mass. The center-to-center distance is 2 centimeters. One ball has a charge of positive 10 nanocoulombs. The other has a charge of negative 10 nanocoulombs. The rod is held in a 1 times 10 to the 4th newtons per coulomb uniform electric field at an angle of 30 degrees with respect to the field and then released. What is the initial angular acceleration? Well, the knowns is this is a dipole. The mass is 1 gram. The distance, the separation distance, is 2 centimeters. Q is 10 nanocoulombs. E is 1 times 10 to the 4th newtons per coulomb. And the initial angle is 30 degrees. You'll probably want to convert these to SI. The unknown is what is the angular acceleration in radians per second squared. Physics of this is torque rotational inertia. Formula, tau equals QSE sine theta. Tau equals I alpha, where I is mr squared. Of course, r is then s over 2. We solve for angular acceleration alpha. The initial angular acceleration alpha naught is 2qe sine theta naught over ms. So that is 2 times 10 to the minus 9th coulombs, that's the charge, And 1 times 10 to the 4th newtons per coulomb, that's the electric field, sine of 30 degrees for the angle. And the mass is 0.0010 kilograms. And the distance, the separation distance, is 0.020 meters. The answer is the initial angular acceleration is 5 radians per second. Dipoles in a non-uniform electric field. Suppose that a dipole is placed in a non-uniform electric field, such as the field of a positive point charge. The first response of the dipole is to rotate until it's aligned with the field. Once a dipole is aligned, the leftward attractive force on the negative end is slightly stronger than the rightward repulsive force on the positive end. This will cause the net force on the dipole to be to the left, toward the point charge, so the dipole will have a tendency to migrate toward the left. Now, this is a video of dipoles in a non-uniform electric field. The dipole near the negative point charge is also attracted toward the point charge. The net force on the dipole is toward the direction of the strongest field. Because the field strength increases as you get closer to any finite-sized charged object, a dipole will experience net force toward any charged object. This does not happen in uniform electric fields, such as that between the two oppositely charged plates of a capacitor. So I'm going to let this run a little. Okay, the water molecule H2O has a permanent dipole moment of magnitude 6.2 times 10 to the minus 30 coulomb meters. The water molecule is located 10 nanometers from the sodium ion in a saltwater solution. What force does the ion exert on the water molecule? The knowns is a P equals the dipole moment, which is 6.2 times 10 to the minus 30 coulomb meters. R, which is the S, that's the separation, is 10 nanometers. Q is positive E. The unknown is what is the force in newtons. Physics of this is a Coulomb's law in a dipole. The formula is F equals QA. For a dipole, the electric field is approximately equal to K times 2P over R cubed. Force equals 2 times K times E times P over R cubed. So it is 2 times the K of 9 times 10 to the 9th Newton meter squared per Coulomb squared. The charge on the electron is 1.6 times 10 to the minus 19th coulombs. The dipole moment is 6.2 times 10 to the minus 30 coulomb meters. The radius, which of course there had to be cubed, that's the separation distance, is 10 times 10 to the minus 9th meters, and that has to be cubed. So the force is 1.8 times 10 to the minus 14 newtons. This force is about 10 to the 11th times larger than the size of the Earth's gravitational force on these atomic particles because gravity is so very weak. Forces such as these cause water molecules to cluster around any ions that are in solution. This clustering plays an important part in the microscopic physics of solutions studied in chemistry and biochemistry. And this is one of the reasons water is called the universal solvent, and it'll dissolve just about anything. It especially loves to dissolve salts. Thank you.